Quantum technology is presently amazingly popular. The United States and the United Kingdom have made it a national initiative. The European Union has a quantum technology flagship. India has a national mission, and China has announced they'll put quantum technology into their next 5-year plan. What is quantum technology and what impact will it have on our lives? That's what we will talk about today. The quantum initiatives differ somewhat from nation to nation, but they usually contain research programs on 4 key topics that I will go through in this video. That's quantum computing, the quantum internet, quantum metrology, and quantum simulations. We'll start with quantum computing. Quantum computing is one of the most interesting developments in the foundations of physics right now. I have talked about quantum computing in more detail in an earlier video, so check this out for more. In brief, quantum computers can speed up certain types of calculations dramatically. A quantum computer can do this because it does not work with bits that have values of either 0 or 1, but with quantum bits, qubits for short, that can be entangled and can take on any value in between 0 and 1. It's not an accident that I say between instead of both. I think this describes the mathematics more accurately. Either way, of course, these are just attempts to put equations into words, and the words will, in the best case, give you a rough idea of what's really going on. But the bottom line is that you can process much more information with qubits than with normal bits. The consequence is that quantum computers can do certain calculations much faster than conventional computers. This speed up only works for certain types of calculations though, so quantum computers are special purpose machines. The theory behind quantum computing is well understood and uncontroversial. Quantum computers already exist and so far they work as predicted. The problem with quantum computers is that for them to become commercially useful, you need to be able to bring a large number of qubits into controllable quantum states, and that's really difficult. Estimates say the number we need to reach is roughly 1 million. Details depend on the quality of qubits and the problem you're trying to solve. The status of research is presently at about 50 qubits. Yes, that's a good start. But it's a long way to go to 1 million, and there's no reason to expect anything resembling Moore's law will help us here, because we're already working on the limit. So the major question for quantum computing is not, does it work? We know it works. The question is, will it scale? To me, the situation for quantum computing today looks similar to the situation for nuclear fusion 50 years ago. 50 years ago, physicists understood how nuclear fusion works just fine, and they had experimentally checked that their theories were correct. The problem was just to make the technology large and still efficient enough to actually be useful. And as you all know, that's still the problem today. Now, I'm positive that we will eventually use both nuclear fusion and quantum computing in everyday life. But keep in mind that technology enthusiasts tend to be overly optimistic in their predictions for how long it will take for technology to become useful. The quantum internet. The quantum internet refers to information transmitted with quantum effects. This means, most importantly, the quantum internet uses quantum cryptography as a security protocol. Quantum cryptography is a method to make information transfer secure by exploiting the fact that in quantum mechanics a measurement irreversibly changes the state of a quantum particle. This means if you encode a message suitably with quantum particles, you can tell whether it has been intercepted by a hacker because the hacker's measurement would change the behavior of the particles. That doesn't prevent hacking, but it means you'd know when it happens. I made an entire video about how quantum cryptography works, so check this out if you want to know more. Today, I just want to draw your attention to 2 points that the headlines tend to get wrong. First, you cannot transfer information faster than the speed of light with the quantum internet or with any other quantum effect. that quantum mechanics respects the speed of light limit is super basic knowledge that you'd think every science writer knows about. Unfortunately, this is not the case. You see this over and over again in the headlines that the quantum internet can supposedly beat the speed of light limit. It cannot. That's just wrong. And no, this does not depend on your interpretation of quantum mechanics. It's wrong either way you look at it. No, this is not what Einstein meant with spooky action at a distance. It's really just wrong. Quantum mechanics does not allow you to send information faster than the speed of light. This isn't the major issue I have with the coverage of the quantum internet though, because that's obviously wrong, and really, what do you expect from the Daily Mail? No, the major issue I have is that almost all of the articles mislead the audience about the relevance of the quantum internet. It's not explicitly lying, but it's lying by omission. Here's a recent example from Don Lincoln, who does exactly this, and pretty much every other article you'll read about the quantum internet goes somewhat like this. First, they will tell you that quantum computers, if they reach a sufficiently large number of qubits, can break the security protocols that are currently being used on the internet quickly, which is a huge problem for national security and privacy. Second, they will tell you that the quantum internet is safe from hacking by quantum computers. Now, these two statements separately are entirely correct, but there's an important piece of information missing between them, which is that we have security protocols that do not require quantum technology but are safe from quantum computers nevertheless. They are just presently not in use. These security protocols that, for all we currently know, cannot be broken even by quantum computers are somewhat confusingly called post-quantum cryptography, or in somewhat better terminology, quantum-safe cryptography. This means that we do not need the quantum internet to be safe from quantum computers. We merely need to update the current security protocols, and this update is already underway. For some reason, the people who work on quantum things don't like to draw attention to that. Quantum metrology. Quantum metrology is a collection of techniques to improve measurements by help of quantum effects. The word metrology means that this research is about measurement. It's got nothing to do with meteorology, different thing entirely. Quantum metrology has recently seen quite a few research developments that I expect to become useful soon in areas like medicine or material science. That's because one of the major benefits of quantum measurements is that they can make do with very few particles, and that means minimal damage to the sample. Personally, I think quantum metrology is the most promising part of the quantum technology package, and the one that we're most likely to encounter in new applications soon. I made a video especially about quantum metrology earlier, so have a look at this for more detail. Quantum simulations. Quantum simulations are a scientifically extremely interesting development that I think has been somewhat underappreciated. In a quantum simulation, you try to understand a complicated system whose properties you cannot calculate by reproducing its behavior as good as you can with a different quantum system that you can control better, so you can learn more about it. This is actually something I have worked on myself for some years, in particular the possibility that you can simulate black holes with superfluids. I will tell you more about this some other time. For today, let me just say that I think this is a rather dramatic shift in the foundations of physics, because it allows you to take out mathematics as the middleman. Instead of modeling a system with mathematics, either with a pen on paper or with computer code, you model it directly with another system without having to write down equations in one form or another. Now, quantum simulations are really cool from the perspective of basic research because they allow you to learn a great deal. You can, for example, simulate particles similar to the Higgs or certain types of neutrinos and learn something about their behavior, which you could not do in any other way. However, quantum simulations are unlikely to have technological impact anytime soon, and what's worse, they have been oversold by some people in the community. Especially all the talk about simulating wormholes is nonsense. These simulated wormholes have nothing in common with actual wormholes that, in case you missed it, we have good reason to think do not exist in the first place. I'm highlighting the wormhole myth because, to my shock, I saw it appear in a White House report. So, quantum simulations are cool for the most part, but if someone starts babbling about wormholes, that is not serious science. I hope this quick summary helps you to make sense of all the quantum stuff in the headlines. This video was sponsored by Brilliant, which is a website and app that offers interactive courses on a large variety of topics in science and mathematics. Brilliant is a great starting point if you want to know more about quantum mechanics. They have you covered on the math behind quantum mechanics, such as linear algebra and differential equations, and they have courses on the properties and behavior of quantum objects and even on quantum computing in particular. To support this channel and learn more about Brilliant, go to brilliant.org/Sabine and sign up for free. The first 200 subscribers using this link will get 20% off the annual premium subscription. Thanks for watching. See you next week.